Is everybody ready? Yes. More OS class. All right. So today we're going to continue our discussion of our understanding of the topic of concurrency, our second of three major topics. And like I said, the most intellectually rigorous, because the way we think about concurrent programs is it's not natural for us. It's not just one step after the other. That's hard enough. Concurrent programs explode that into a very, very broad space of crazy things that could happen to the point of it feeling like the computer is behaving randomly, even though each little individual thing is not random. And as a result, it's kind of a skill we need to acquire, how to think about writing correct concurrent programs, and then how to build OS and hardware support to enable people to build correct and high-performance concurrent, maybe parallel programs. So what we're going to do today, so this is continued, and what we're going to do is we're going to we're going to pick up where we left off. So we will finish the kind of intro of this topic, where we will learn about the notion of a basic lock as a solution to this data race problem, or what sometimes people call the mutual exclusion problem, and we'll see why it's called that. So we'll understand that in a little bit more detail. Then we'll look at a couple other code examples where we can understand how to think about adding locks to different types of code. So far we've just looked at a very trivial example where you put a lock around the increment of a counter. So we'll look at a few different examples. And then what we will start to do is get into how to build locks using different hardware primitives. It turns out in the very earliest of computer systems, people realized that to build a lock required a little bit more powerful of an instruction than we're used to. We're used to instructions like load something from memory, store something to memory from a register. We're used to adding two numbers together, branch. We need a slightly different type of instruction from the hardware in order to effectively build a lock. And so we're going to talk about that, what those instructions are like, and then show how to build locks so that people can use them with those different primitives. So that'll be our focus for today, and let's see how far we get. I'm always ambitious in how far we'll get, and then reality intrudes. Actually, what has been great is the number of questions from the class has been terrific, so I encourage you to keep that up. For me, it's particularly great because I already know what I'm going to say, so the questions are always the new part of the class for me and the most fun, therefore. And it also helps shape, sometimes helps shape, like I said, the future classes as well. Certainly all the questions over teaching this class for 18 years have 100% changed what's taught in here. So as you continue to ask questions, you are kind of, paying it forward. You are making future classes better by helping to shape it today. So thank you for that. Okay, so let's go and look at some code again. What we're going to look at here is this example, and I'll just don't need that. Let's quickly review what this code does. In the main, we talked about a multi-threaded program as being very similar to our classic running program or process, which we'll now call a single-threaded process. But we are able to create these different activities which are ongoing inside of this program concurrently at the same time. That's why we call it concurrency. The main thread, when it starts up, it is our first thread of execution. We think of a thread as being associated with its own program counter, its own set of registers, its own stack, and then a shared heap with other threads, and maybe shared code, of course. And then we can call pthread create. In this example here, we call it twice to make two more threads for a total of 3 threads. And then when we create a thread, the important pieces here are we specify which function do we start running this thread, where do we start running, and what we also do is pass it some kind of argument. So here we just pass a string A or a string B. So that's pthread create. It's going to create two threads. And then the main thread here doesn't do anything very interesting. It just waits for those two threads to finish running. So hopefully it's starting to make a little sense. It's a little strange, but it's hopefully, given your understanding of OS mechanisms, hopefully not that strange. A thread is something that is known to the operating system. And sometimes people call it, for that reason, they call them operating system threads or kernel threads. There is a different way to make a thread package called a user level thread package. We're not really going to talk about those for various reasons. But for kind of the short story there is that would be something where you're creating the illusion of having multiple threads running at once, but the OS doesn't know about it. So the OS scheduler just sees it, for example, a single process. Here, the OS knows about each of these threads and schedules them. So it might decide to run one thread or the other or the main thread or, of course, some other process entirely when this program is running. And it's up to the scheduler to decide when things happen. So any questions about that? Just getting us back on the same page, yeah. Great. So the question is it the same process scheduler or is there something else going on? No, there's nothing else going on here. It's just a scheduler that knows about the runnable entities in a system with threads like Linux or any other modern operating system. They have in all their, like the process structure there will be more complicated. It'll say, oh, what are the threads of this process? And the scheduler will be aware of all those things and then schedule among them. And it can use any of the scheduling disciplines that we've talked about, from simple things like round robin to a multi-level feedback queue to whatever else, a lottery scheduler. All of those things are possible. Make sense? Okay, hopefully not too strange. And then we were up here, and we saw in this particular piece of code what I claimed was a race condition, a place where multiple threads were going to access a shared piece of data. That shared piece of data in particular was just a counter that we were updating, and they were racing to update it. If they're just reading it, it wouldn't be so much of a problem. So it's a combination of having multiple threads accessing some sort of shared data. This is the simplest form of this, a global counter called balance. And it was a race, and particularly what we saw, or what did I call it, scratch or something? Yes. What we saw is when you really break down what's going on at the instruction level, at the assembly level, the instructions that are going on are to just simply increment a counter are these three instructions. We're loading the value from memory into a register, we're then incrementing the register, and then we're storing the value back from a register into the actual memory location, the shared memory location. And what we saw is why this didn't work very well was because each thread could very simply, at the same time, essentially get the old value, each incremented independently, and then store it back without incrementing it, in this case, twice. So you could essentially lose an update, and your value would be lesser than what you saw, what you expected it to be. So you get a bad outcome. Any questions about that? What's really interesting, so as you think about a question, what's really interesting about that is that it has something to do with the power of instructions, right? Instructions are these powerful, you can think of them as atomic transitions of the state of the CPU from one state before the instruction ran to the state after the instruction ran. Of course, interrupts can happen between instructions, which means that at any given point, a thread may be interrupted by a timer interrupt, and a scheduler may decide to switch entirely to a different thread through the virtualization techniques we've talked about already. And it's that problem, the fact that we have these small instructions and that they're not doing the entire thing that we want at once, they're doing it in steps, and the fact that that can get essentially interrupted and allow some other thread to run, that leads to the problems that we're having. Any questions about that and how that kind of makes sense? Yeah. Oh, you're saying like what commonly causes this kind of this problem to occur essentially? Well, the problem occurs for two reasons. One, it'll occur on a single processor because really any interrupt that could lead to a scheduling change, this could cause this problem. So that could be a timer interrupt. But if you have an I/O intense workload, which we haven't talked about, one that's doing a lot of disk I/Os or SSD I/Os, that's going to cause a lot of interrupts too. And those are opportunities for a scheduler to do something and change what's running. So it's hard to say generally, but certainly any interrupt can cause a problem on a single CPU. On multiple CPUs, if we have operation going on in parallel, clearly this just is going to happen more readily. And that's why the example shows up actually so easily on my machine, because I'm running on multiple CPUs, and you don't have to have like just the perfect timing of an interrupt for this to occur. It just happens because they're running at the same time and kind of getting the values that you would naturally get by reading the shared balance at the same time. Okay, so let's see if we can make a little progress. Let's look at the code again. The kind of natural fix here, which we'll just do the kind of perhaps a more realistic fix, is to put this new primitive that we're introducing called a lock around the part of the code that we know is a critical section. So you can see here already there's going to be a burden. The burden right now on someone writing a concurrent program is to know where in the code these race conditions might exist, to identify those, then to essentially mark in the code those sections by putting a lock and an unlock around them, and therefore get the behavior that we want. Now we're going to talk about that exact behavior in a second, but that's kind of the basic idea. So then let's talk a little bit more about, what does this do? We talked about it a little bit last time, but let's make sure we understand it. Then we're going to talk a little bit about how to build a lock. Then we're going to do some examples, like I said, and then we'll come back and build a lock in more detail. So why does this problem occur? We have multiple threads running, and the problem is really that we're allowing multiple threads into this critical section at the same time. If we just allowed one at a time into that critical section, they would read the value, update it, increment it, and then store it back to memory, and then maybe let somebody else do it, some other thread do it, and then it would proceed as we would expect. It was only if we got interrupted while we were doing it that this problem arose. So what a lock is trying to do is basically guarantee that behavior. It's trying to guarantee what we would call mutual exclusion, right? It's, so let me write that down, mutual exclusion. And what that means is one thread, when it holds the lock, that's a term we'll use, that if you've acquired the lock or when you hold the lock, you exclude others from being able to hold the lock and therefore exclude them from entering this code. So what that means is when the lock is not held, in other words, when it's free, pthread, what we want for this pthread mutex lock to do, this should return immediately. And the lock should become held. But when the lock is held, what this should do is basically the thread should get, let me put thread in here, should get stuck here until the lock can be acquired. So does that make sense? A bunch of threads are created. They're both trying to acquire the lock. Somehow one of them does. We'll talk about how that happens internally in a second. Somehow one acquires the lock. Then it goes ahead and goes into the critical section. At that point, if an interrupt can still occur, generally, and so an interrupt could occur, which means that that other thread could get scheduled, it'll try to acquire the lock, and it will fail. It'll just sit there and wait. And then only when that first thread who has the lock gets to run again, releases the lock, will the other thread be able to enter the critical section. So let me draw that over here. So we have thread 1 and thread 2. They're both trying to enter the critical section, but thread 1 runs first for some reason, so this is time. And it acquires the lock, which you notice I called very cleverly lock. A pthread mutex t is just a variable type, of which is a lock. And so I'll say a mutex or a lock, and I'll say those things interchangeably. You'll have to kind of get used to that. And we can have, of course, more than one lock for a program. Some programs will have many, many different locks. We'll talk about that a little bit more today. But here we just have one lock. So in our example here, we acquire this lock. So now it's acquired. And then we're running along here, and we're in this critical section. But it could be that even though we're in the critical section, that part where we're updating balance, that an interrupt could occur, right? This could be an interrupt here. And the scheduler isn't really aware of what's going on in your program. It just knows generally, at least in this simple examples, it just knows, well, sometimes you run, sometimes thread 2 should run, sometimes thread 1 should run again. So it might switch and run thread 2. Thread 2 then starts running and tries to get the lock, but it's stuck. And that's how we're going to guarantee the correct behavior. We're not going to allow thread 2 in the critical section while thread 1 is in that critical section and holds the lock. So it'll sit there maybe for a short while, maybe for a long while, and that actually depends on the implementation of the lock, which we'll see in a minute. Another timer interrupt will occur, timer interrupt, let's say. Then we'll switch back, and we can see this critical section is actually going to become longer. We'll switch back over here, and we'll continue until this thread calls unlock, at which point another thread would be free to possibly acquire the lock. So the critical section actually extended all the way until we were done. So from between the lock and the unlock. That's the critical section. So does that make sense? The basic idea is actually pretty simple. It's really just identify in your code places where data is getting updated by multiple threads and make sure you have some kind of synchronization primitive, or a lock, as we call it more simply, around that code, a lock and an unlock. Yeah?
What is regulating the locks?
Yeah, we're going to talk exactly about it. This will make one more degree of sense in a second when right now it's magic. How do locks work? We call that function, at some level of programming, you could just treat them that way and it would work if you used it correctly, but you wouldn't know how it works. Here in OS, unfortunately, we have to learn how things work, but this is actually our great benefit of being in the OS class. And we'll be doing that in just a moment. Yeah? Yeah. So the question is, by the way, how well can people hear other students' questions? I've been kind of assuming it's worth repeating them. Is that correct? Okay. Now I forget. No. His question was a good one, which is when in our example that we had here, when thread, let's highlight this a little bit. When thread 2 came down here and started running, and then it tried to get the lock, clearly it can't get the lock at that point. So essentially running thread 2 any further at that point is kind of a waste of time. Whether the scheduler knows about that or not depends on how you build the lock. And we will see at first the scheduler won't know a thing about it, and that leads to a certain kind of behavior from locks, which isn't so great, but has some other good properties too. And then later we'll see how to integrate that with the scheduler a little bit so the scheduler can do a smart thing, which is, for example, when you try to get a lock and can't, immediately switch to somebody else that might get you towards getting through that critical section and so forth. So you're kind of a little bit ahead of us there with the question, but we'll catch up. Yeah. Yeah, so I think it's kind of the same question, which is when T2 tries to get a lock and then gets stuck, does that immediately cause some scheduler activity to happen? The answer is maybe. It depends on how the lock is built, and we'll see in a second how that goes. So let's just hold off on that question. Other questions? Yeah. So kind of, should you have threads that are very arrogant and think that they should run instead of the lowly, low priority threads? That's a great question, and I think I'll also defer that to the future a little bit. This occurs all the time when you have a priority-based scheduling system. You have a high priority thread, and then you have a low priority thread, and it's possible they're contending for the same lock. So then you have this actually even a weirder situation, which you're kind of hinting at could happen, which is the low priority thread grabs the lock, and then the high priority thread gets to run, but actually wants to grab that lock, but can't. And then what do you do? So how do you deal with that situation? That's called priority inversion. It's the fact that the lower priority thread basically is kind of taking over the system or kind of preventing progress from happening by acquiring a shared resource. We'll talk about that eventually, but we won't talk about that right away. All very good questions. Okay, so it sounds like people just want to go ahead and make progress since we're asking questions about the future. So now what we're going to do is try to build our first very simple lock, and it's called a spin lock. We'll see why it's called a spin lock in a second. So let me write that down first. So let's try to build a lock, spin lock. Famous lock, probably the first lock that was built was a spin lock. As far as I can tell, it's one of these, history of computing, it's kind of a great time to do history of computing because like the people who invented the early things, a lot of them are still alive. Soon that won't be true. That's a sad fact. But some things are a bit murky because industry didn't document everything that they built, so it's sometimes hard to find the exact history. But certainly by the early 60s, a spin lock existed, is what I would say. And then by the 70s, papers were being written about it, but it was certainly existed before then. So let's try to think about the intuition of how we would build a lock. First, we need some state. The state is going to tell us something very simple, like is the lock held right now, or what we sometimes call acquired, or is it free or not acquired? Right? So we need essentially one bit of information about each lock that we have in our system. So the way we will do that here is we'll just have some sort of integer, like an integer. And we can call it whatever we want. Let's call it mutex. Excuse me, losing my voice. So that's the easy part, mutex. And of course, we'll generally want to initialize it to being free. Not often do you want to start with it being locked. So maybe we would set it to 0, and 0 would actually be free. And then that implies, of course, 1. 1 is that the lock is held. So now, what we want to do, all we're trying to do in this next part of class is define how those functions, mutex lock and mutex unlock, would work. That's it. Just given that we have a variable, so you can imagine somewhere inside of this pthread mutex t, there's an integer or something that says, is the lock held or not? It's not visible to us right now, but you can imagine that. And then what pthread mutex lock and pthread mutex unlock must do is change that value and get the desired semantics of the locking functions, which is when many threads try to enter, only one can acquire the lock and then prevent others from acquiring the lock until that first thread frees the lock. So let's think about how to write these routines, and I'll just do that over here. So I'll just call it mutex lock is the function that we're trying to write. And I guess, well, maybe we'll do this a little bit. Well, okay, we can. What I often do is that we actually define our own, let me just go ahead and do this. What we end up doing here is we're going to define our own structure, which will mirror the pthread mutex t structure. So let's just do something that mirrors that. So let's say we have a struct, mutex, or something like that, struct mutex, and all it has inside of it now is, well, let's just, you know what, I'm going to change this a little bit. I'm going to get rid of this, and then what I'll do is I'll say we'll just call it lock in there, and this part's still true, so I will keep this. This is important to remember. And then what we need to do is, before we do this, let's go ahead and just have a mutex init, which takes a struct mutex, let's say pointer m, It's important to initialize locks, by the way. A very common bug is to not initialize the lock, and then the program behaves strangely because it didn't get properly initialized. So in pthreads, you see how we do it here. We use this what's called the static initializer. We set the lock equal to pthread mutex initializer. There's also a pthread mutex init function you could call to call it dynamically, but you'll get to that eventually. And so here, all this code is going to do is set lock equal to 0. So this, it's free at first. Okay, and then the same thing down here. We're going to pass in our struct mutex, a pointer to that at least, and we want to write our lock function, and I'll leave a little room for that. So I'll go ahead and do that. So now what we're going to try to do is develop an intuition for how this is going to work, and how this is going to be problematic, but let's go ahead and try to do it anyway. And this is going to get to the root of why it's called a spin lock. Okay, you'll see why it's called a spin lock. So while the lock is held, what we're going to do when we enter this function is we're going to spin. That's a semicolon, and this is just then our loop. So while the lock is held, we're going to spin. The moment that we notice that the lock is no longer held, what this function is trying to do is acquire the lock. And this is going to be our first attempt at writing a spin lock. Now, it's not a correct implementation, warning, but it hopefully gives an intuition. And then, of course, we'll do one more piece here, which is we'll write our mutex unlock function, which again takes a struct mutex star, and to unlock, all we're going to do is set the lock to free. So this frees it. This hopefully acquires it. Now your tingly sensation of something's wrong with this code should be taking place right now. Something might feel wrong if you start thinking about this like the evil scheduler that's trying to get something bad to happen. Usually to think about concurrent code and execution, and here we want to think about many threads calling mutex lock at the same time. We have to think about it at the assembly level, but here it's sufficient to think about it at the level of C because the problem should be apparent. So why don't you do this actually, just to make sure we fully force ourselves to go through this mental exercise to the extent that I can force you to do something, which is not that much. But talk with someone around you. If you don't know anyone around you, introduce yourself. Spend 1 minute and convince yourself that there's something wrong with this code and convince yourself what it is. All right. So there's a problem. Who feels good about knowing about what the problem is? Who feels like, yes, I definitely know what the problem is? 2 people confident. Who feels like they might know what the problem is? Has a guess? Maybe. Okay. So the way to think about this, of course, is what we've already talked about, which is if two threads were running this and you could kind of interleave their behavior so that you could run a little piece of one thread and then run a little piece of the other thread, how would you run a little bit of code in each so as to cause a problem? And the problem here, of course, would be that two threads think they acquired the lock, not just one, right? Our guarantee has to be that when two threads enter this at the same time, that only one thread returns with the lock and the other gets stuck. And in this case, it would get stuck spinning, right? Stuck spinning, yeah. Yes, that's correct. Yes. I shouldn't have said anything about that before. So in any case, that is exactly right. So who wants to share some thoughts with it? Where can we, if we were being cruel to these two threads, where would we let one run and then stop it and then switch to the other one and move it forward so that we cause a problem? Where's kind of a critical point in this? Yeah. Yeah, so what could happen? Yeah, exactly. So if thread 1 came in here, kind of did this part of the code we'll call the test. You know, it's testing if the lock is free. It could do the test. It'd say, oh, the lock is free. Then it's about to do this acquisition of the lock, but it gets interrupted. Then test 2 comes in, thread 2, sorry, comes in, does the test as well, also finds that the lock is free. And now we have two threads that have both tested the lock and they've both found it to be free. They both then, foolishly acquire it. They set it, right? So this is often called the set. This is the test, this is the set. And at that point, we have a problem. We've broken mutual exclusion. We have not guaranteed that only one thread executes inside the critical section. All the problems that we had before can happen because we have the same exact race condition inside of our mutex lock function. Right? It's the same kind of race. We have a shared variable. We're trying to update it together. Does that make sense? Questions about that? It's really important to understand what's going on in this little piece of code. Again, remember, concurrency makes us all feel bad because we're staring at literally 3 lines of C, generously 3 lines of C code. And it's hard to understand exactly what it'll do. So that's okay that it's hard, but we have to understand it. There's a question? Make sense? Okay, so let's move forward a little bit. So the problem, if we were going to summarize it, is that we needed to do a test and we needed to do a set. But we wanted to do these atomically. Essentially, that's a fancy way of saying kind of all at once. We wanted the testing and setting to happen at the same time. Like if the test, if the lock is free, then immediately acquire it. And if it's not, okay, I'll wait. But if it is free, immediately acquire it. Don't do that as the next instruction. Do that as part of this instruction. And so what this hints at is that we need a more powerful instruction. From the hardware. More powerful instruction from the hardware. And this instruction has, like I said, existed for forever. And what sometimes it's called is the test and set instruction. Or it's sometimes called simply, like on x86, it's called the atomic exchange. And now what we're going to see is how to use it in order to build a simple spin lock. So I'm going to switch to this other screen. I'm going to switch to main thread, let's call it 3. Oh, this is 3 is the bad code, so this doesn't work. And then main thread 4 shows you what the exchange instruction looks like. So a couple points in this code here. exchange is the Intel instruction we're going to use. Let's ignore this magic right here, so ignore this for now. That's actually how in C code you can include with this directive, ASM directive, inside of this inside of C code, you can actually include a piece of assembly code because this is a real instruction we're going to want to include. But what we should look at is the very top, which is how exchange is defined. Okay. So how is exchange defined? Exchange is defined as follows. It takes two parameters, which is an address to an integer, which for example would be our lock, and then it takes a new value. Okay. And what it does is very simply this, and it does it all at once, this atomic powerful instruction, is it returns the old value that's pointed to by address. So it gives you what was there before, and then at the same time, it stores the new value into that location. So you're given an address, and it says, I'm going to give you back what was there before, and I'm going to take the value, this new value you have, and I'm going to store that there at the same time atomically. And what my claim is that's enough in order to implement this spin lock, which we were calling mutex lock in the code I was writing on the iPad. It's called spin lock and spin unlock here, but they're all the same thing. So now your next challenge, and then we'll call this challenge a break. So we'll make it a little longer. So let's give you like 4 minutes here. And then what you're supposed to do is write the 3 lines of code, 2 lines of code, and 1 line of code that use exchange, like you can call it that function exchange just like the prototype shows you up there. Use that inside of spin lock in order to acquire the lock atomically that we have, okay? And we can, again, you have, here we're just using an integer. In the example, we're using, a part of a structure. Either is fine, the idea is the same. So let's take a long break where you do a little bit of work and a lot of break, or vice versa. And we'll come back in 5 minutes and talk about that, or 4 minutes.
we should build a hardware support for even that we have exchanged multiple CPUs that will still speed up. So
Atomic hardware gives you an exchange
because with
instruction.
two CPUs both doing exchange somehow magically happen. So one
It absolutely happens, and it has to be correct across multiple CPUs.
yeah, so it seems logical. I feel that there should be maybe a special mechanism so that other processors as well request a lock from the special entity, so that the entity schedules this lock request response. And this entity is defined specifically.
Essentially,
Yeah.
in many cases, the hardware can support this fairly efficiently. But there are a few cases where your idea actually would work. I could actually point you to a research paper about that. But just to be clear, this in hardware, people know how to build things like this. It works pretty well across multiple CPUs. Because CPUs, you have to take 552, you have to take 752, you have to take 757, then you'll understand how the hardware works. Then you can understand how the CPUs are ultimately
Because I feel like that
if you want, I can point you to papers about it.
philosophically or logically, I feel that there should be someone maybe manage so that
Yeah, but
coming
your
one
intuition isn't quite right because in most cases there's not a lot of convention and then you're just adding overhead to make things slower.
so since there are very few cases that
Yeah, so there are a few cases where you want to monitor that connect carefully, but we'll see how to build one that works pretty well without that. We'll get to that soon. Yeah. I mean, this is like literally how to implement an exchange.
Oh, okay. So you okay?
That is the exchange instruction. This is how you specify it in Intel's syntax,
Okay.
and this is how we call it from C. And but the details of explaining what the input-output operands and other what fields are is a bit involved. So I'm just kind of it's magic. Right?
Okay. So technically, like this exchange isn't
That,
atomic.
no, this exchange is atomic.
Oh, it is.
It really works.
So if we
If
had.
you use exchange like that,
Oh, okay.
it 100% will work.
How would you do some like time analysis with the current program?
Yeah, it's very hard. I'm not going to answer that.
Okay.
Yeah. Okay, we should get going. Welcome back. I realize I have a bit of a timing problem with this class, which is what I want to do, and I don't know how okay this is, but what are they going to do? Fire me? So what are you going to do? Be really unhappy with me? I want to make Tuesday a little shorter, not a lot shorter, a little shorter, and Wednesday a little longer, because we've been kind of going 50 minutes in here. I don't know if that's okay with you. If it is, I would prefer to do that. If it's really a problem, then I'll probably still do it. But I suspect that the experiment of too much on Tuesday and too little on Wednesday is being proved out as it's just challenging for students to suffer through that much on Tuesday. So anything that's a little less Tuesday, and I see the questions, I'll get to them in a second. Anything that gets to is kind of a little more balanced, hopefully will be better. But let's hear some comments about why I'm wrong or why I'm right. How much less on Tuesday? I was thinking about I was going to do a time neutral, so we're scheduled at. I mean, it's kind of weird how we're scheduled, honestly. It's scheduled 5:30 to 8:30, which is just too long. And then today is actually we have the room from 5 to 6:30 or 5 to 6:15, but I've been kind of running short of that, like to 5:50 or something. So I'd really like today to go to maybe 6:15 and then take exactly those minutes out of Tuesday. So we definitely end by let's say 8 or something like that. Or even we could get a little close. We could even make that a little shorter if we're really I don't know, energetic. Unfortunately, that opposite happens during that class. So I don't know. Why don't you think about this? If it's okay today, I'll run a little bit longer. If it's really a problem, then we will figure out how to deal with it. Yeah. No, were you saying this is great? Okay. Just go with it now anyway. And anyway, my hope is therefore to get a little bit more like, and then use the second half or last third of the Tuesday is more kind of the actual discussion part of the class. So I hope that's okay. I'll perhaps ask on Piazza or even threaten to before, but now I actually will. And then you can register your opinions at that point. As I said, I'm taping everything, and you know, in the worst case, if you can't make it, I know some people can't even make this session because I think some CS classes overlap this time. Is that correct? Which classes, by the way? 368. Yeah, okay. You can skip that. What other classes? Does anybody know? I mean, you're all here, so either you're skipping it and you don't want to say, or okay. So I'll ask about that. Did you have a question too? That sounds great. It's actually the case where too much time was scheduled. It's longer than you usually would suffer through 537. I shouldn't tell you that. But so we'll just basically then, if that's true, we'll accept that as truth and that most people think that, and then we're just going to shorten Tuesday. So just a pure victory for you. Okay. So who's going to help us? Let's get back to this, and let's just try to get through whatever we can today. Okay. Now unfortunately, we have to focus again. So my apologies. Who has an idea of what to do here? Okay, what?
So in the spin lock
Yeah.
function, we have that same while loop with the spin.
Yeah.
And the condition, you would make the exchange call with the M arrow lock, and the second argument would pass it on.
Great. So the intuition, if you couldn't hear it, was that you use exchange in that while loop. Remember we had let's quickly flip back over here. We had this test, which is we're trying to do, and we're trying to do this setting. And what you kind of notice about the atomic exchange is it does both of those things. So we can use essentially the same loop here, but we're going to replace the testing with the exchange instruction and therefore achieve what we're trying to achieve. So let's go ahead and look at that. And by the way, this is, so this, this is C code that you can call this exchange function. It's actually ripped essentially straight out of xv6. So if you play around with the locks inside of there. And then, do you guys have a question? Is there a question here? No? Okay. Here's the code that we're looking at. That's my nice way of asking, can you guys stop talking, by the way. So, if you have a question, though, I'd be happy to take it. So I just, at some point, it's a bit harder with larger classes, and a little bit of talking here and there is totally fine. But if it keeps going for a while, then you can start seeing, you may notice I completely start losing my train of thought. And so do the people around you, unfortunately. So it's not just a local effect. So try to, find balance in life as well as in talking in class. So in any case, that exchange function, that C function, is actually going to turn into just a single assembly instruction, which means we can use it as just like to build a real synchronization primitive. So this is working code. And the spin lock is simply implemented by just calling while exchange lock and 1 is equal to 1 spin. So let's make sure we understand that. If a thread comes through and enters that while loop for the first time, it's going to call exchange, and it's going to, remember, set the new value, right? It's going to set the new value to 1. So it's immediately going to become locked. And it's critically going to return the old value the first time this gets called. What is the old value? It's 0, right? The lock was free at the beginning. So it's going to return 0, which is not equal to 1. So the first thread through here will not spin. It'll just fall out and have acquired the lock, right? So it set it to 1, it returned 0, and it acquired the lock. Then to kind of undo that, you can just set the lock to 0 here. We use exchange to do that, but it's probably not necessary. You could just set it to 0, or just star lock equals 0. simple as that. That's a spin lock. And of course, if a second thread enters, think about what's happening. This is a little bit the weird part here, is it feels like that other threads are messing with the lock. Because what they do is they're calling exchange repeatedly, right? A second thread enters, and what it does is it calls exchange. It overwrites the lock, which is already held with 1, with the value 1, which then returns the old value, which is held, so it's 1. And then it just keeps doing that forever, right? For a while at least, until the lock is free. And it just keeps writing oh, it's held, it's held, it's held, it's held. At some point, the lock becomes free, and then some thread in this loop that calls exchange will get a 0 back, set it to 1 atomically, and then acquire the lock. So let's look at that in this world. So again, we have thread 1 and thread 2. Thread 1's running along, it calls lock, it acquires it, which means lock is equal to 1. It did that with a single exchange instruction. It's running along in the critical section. Great. But then it gets interrupted again. And we switch over to thread 2. Thread 2 calls lock, and then it's just going to get stuck in that loop. And it's going to get stuck, and it spins. And it runs for a while, and it spins, and it spins, and it spins. And eventually, maybe 10 milliseconds later, like a time slice, a quantum, a timer interrupt goes off again. And then what we do is we switch back to thread 1, which then runs and releases it. So you can see some problems, and we'll talk about how to address this, not this time, but next time. But a problem with the spin lock is, and if you're unlucky, it's a lot of spinning. What other problems are there with a spin lock? Yeah. Yeah, you said when multiple CPUs are running, you can't prevent the situation. That's not correct. So as I thought I was telling you earlier, exchange is guaranteed by the hardware across even multiple processors to have this behavior. Now, how do you build that? Well, we're not going to, in 5 minutes here, do the summary of 552, 752, and 757, where by the end of that, you have kind of a good idea of how parallel hardware is built and how in the world do these computer architects, amazing, complex, interesting field, how do they figure out how to make an exchange instruction such that if 2 processors execute that at the same time, only one of them returns the old value, gets the thing first, and then the other one is serialized after that. That does happen. That is how the hardware works. This works on multiple processors as well as one. So that's not the issue. Yeah. Yeah, that's a very interesting point. This affects scheduling, right? Because now what we're doing is we're kind of moving a little bit of scheduling into the program itself. And we're basically controlling the scheduling by putting locks in our code. So that's certainly a byproduct, and we want to be careful about that because it could conflict is the verb, conflict is the noun. It could conflict with our other goals that we have with our scheduler. Our scheduler might have, for example, as we mentioned earlier, priorities or something like that. If our thread, the way we build our multi-threaded code changes that, then maybe we don't get the expected behavior. And particular when you're looking at, let's say you have a case when you have, let's say we have many threads. Let's say we have n threads. And let's say they all enter the lock code at the same time. Which will get the lock? And when I ask that question, I mean it at first and later, too. Can we say anything about that? Let's say a bunch of threads are contending for the same lock. It's a term people will use. can we say anything about, let's say you know you have your thread, there's threads 1, 2, and 3. Thread 1 gets it first. Is that necessarily going to happen? Of course, probably not. But once thread 1 has it, can we say anything about when thread 2 or when thread 3 will get the lock? What are they doing? What are they going to be doing? Yeah. Well, it clearly has something to do with the scheduler. But let's say we have this: thread 1, thread 2, thread 3. Thread 1 grabs the lock, and then yeah, it's interrupted at some point. Thread 2 then tries to, but spins the whole time, gives up the CPU, spins uselessly because the lock is still held here. Then we switch to thread 3. It spins, doesn't get the lock. Then we switch back to 1. It then gets the lock. Sorry, we'll continue 1 down here. It releases the lock, but then it reacquires it, lock. Then it runs for a while. Then it gets interrupted. Then thread 2 runs, it spins. Then thread 3 runs, it spins. Can we ever guarantee that even other threads will get the lock with this approach? No, we really can't, right? So a problem here is, as related to scheduling to some extent, is fairness, and even an extreme form of fairness, which is starvation. This lock that we've built, it doesn't even guarantee that you'll get the lock. You could just sit there and spin for a very long time without ever acquiring the lock. And that seems like that might be a problem. We might want to make sure that all threads eventually get locks. Yeah. I thought you said things were nice. Yeah, they are nice, right? They're perfectly nice. Like this code here, right? I mean, how we're implementing the lock, right, the question is, so we have to be a little bit careful how we think about this. Remember, the code that we were really writing was this code. This is just, I've created a bunch of threads, and they're working together to achieve something, and we want to make sure we get the correct result. In this case, balance being updated a bunch of times. So those are perfectly cooperative, right? Now, what we're doing is we're going inside the primitives we're providing to those programs in order to build them so they can achieve their goals. And what we're doing is we're realizing that one way to build this, the simplest way to build a lock, a spin lock with just this minimal amount of hardware support, might lead us into situations where the threads don't get maybe like a fair shake, even though they're working together, right? We want to make it so you write the code in that very simple way, but then the primitives support kind of some of these other properties. Like we don't want to waste a lot of CPU time spinning. That seems like a waste. We don't want to make sure, we want to make sure that any thread that asks for a lock eventually gets the lock. So those are some properties we'll try to provide so make it that the programmer doesn't have to worry about how bad the lock implementation is. So you have to kind of think about it at the right level. Certainly the threads are cooperative. That's definitely the model, and that hasn't changed here. Good question. Other questions? Okay. Does a spin lock make sense? Any other questions about spin lock? Okay. So what we will do, I wanted to do 2 more things, but we're probably just going to do 1 more thing, and then we'll stop at the dreaded 6:15 time. What we'll do now is I just want to make sure we expand our mind a little bit before we go into locks in more detail, and that expansion is going to occur by looking at code that isn't just a counter, right? This example is a trivial example that shows us all the things we need to worry about, but it doesn't show us how to really add locks to code that's a little bit more complex. Well, you'll see it. And for example, you often see locks in interesting data structures that you build if multiple threads are accessing those data structures. If multiple threads can access your data structure safely because it has locks in it and so forth, we call that a thread safe data structure, or maybe there's a library that's thread safe. So if you ever hear that term, it means threads can call into it, and there's some locking inside of it that makes sure that it works correctly despite the presence of multiple threads. So let's look at some code. What should we look at here? Okay, let's look at this code. It's like a little bit of list code. So why don't you stare at that for a minute? This is like a beginning of a little list library in C, and we'll just look at the insert. That'll be our focus, though of course the initialization function is shown there too. Every time you call one of these list functions, you're going to pass a pointer to a list T And in many ways, you'll see code like this all the time in C, which has a flavor of object orientation, right? In every method you pass, though, explicitly pass the struct that is the object, which is the list T, instead of that just being implicit with how you would do it in, say, Java or C++. And then the methods are just functions, of course. But otherwise, it has a similar kind of feel to object-oriented code. And here we just have a very simple insert. So study this code, figure out, make sure you understand what the code does, draw a picture if you need to, and then in 2 minutes, we'll come back and talk about how do we add locks to this code to make sure that it's, or do we need to add locks? That's a good question. And then how do we add locks? Turns out we need to add locks. So sorry, I gave that away. Spoiler alert, we need to add a lock to this code. So how do we do that in a way that's efficient and correct? Okay, so the question makes sense. And you can assume here for simplicity, like when list init is called, that like you already have, like only one thread will call list init, so that you don't have to worry about making that thread say. Multiple threads may call list insert. All right, so since we don't have that much time, I want to get through the list, and I want to get through like a slightly more complex hash table, which actually isn't that complex. Let's talk about this code a little bit. If you were describing this insertion to somebody, what would you say about it? You would say it's a list insertion, but what else would you say? Yeah, sorry, go ahead. Yeah, so why do you say that? Yeah, it's kind of an insert at the front, so it's very efficient. Of course, you don't have to like search through the list to find the end or put it in sorted order or anything like that, right? Just right at the head of the list. So let's and then the question, of course, is down here. If you see the way that the list works, it has a head pointer. It's all that the list is tracking, and that's set to null at first, and then all we do is insert things at the head. And then, of course, when we're writing this code and we're worried about multiple threads calling into it, we have to say, well, if multiple threads call into insert at the same time, is that a problem? Is there a race condition? Seems like yes, because I already answered it yes. So why is that? Can somebody explain? Yeah. Sorry. Great. So I probably couldn't hear that. So the suspicion had something to do with these lines at the bottom. New next equals L head, and L head equals new, and the intuition is correct. It's L head now is a shared piece of data that's getting updated potentially by multiple threads. So what we'll do here is let's just do an example. Let's say we have an existing list. Head points to a node, points to a node, points to null. Okay, head is the thing that is going to get updated eventually. And then what we're going to do is, well, in thread one, the first thing it does, if you look over here, is it calls malloc. Now, even there, you have to ask a question. Is it okay for me to call malloc from a bunch of threads at the same time? And the answer on any modern platform is yes. All mallocs that you call will be thread safe when you create the program with -p thread, for example. So you don't have to worry about like acquiring locks to even go into malloc, because of course malloc internally is it's a big shared heap and has data structures to manage what's free and what's not. So of course it has to be concerned with multiple threads updating it. But let's for now not worry about that. So thread one creates a new node. Its new points somewhere into a heap. Let's just have a new node here. And then we put some key inside of it. Let's put key 1 inside of it. And then you can see what we're doing. We say the next node, here's a next field. We want to point it to here. And then what we eventually do is we want to swap the head to point to what new points to, and thus our new list is created with K1 at the beginning of the list. Okay, that's just a basic list insertion. So let's say we didn't do this step. Let's say we had just gotten through, we did this line of the code, then we did this line of the code. The picture looks like this, but we haven't yet updated head. And then unfortunately, you can guess what's going to happen. Thread 2 is going to come along, and it's inserting K2. It has its own, new in the code on the left over here. New is a pointer to node T. It's on the stack, which means that it's thread local. Each thread has its own stack. So new to thread 1 is quite different than new to thread 2. New here is going to point to a node. We're going to put K2 inside of it. And then because of this interrupt that occurred at this untimely time, we're also pointing it right here, pointing its next pointer to the head. Then maybe what we do is we, let's say we execute thread 2 first. So first head gets set over here. Then the very next line, that essentially gets undone. Then thread 1 runs and says, sorry, buddy, back over here. And so what you can see happen then, if you look at it, is now we have this node that's sitting here that thought it got inserted at the head of this list, but it didn't. So unlike our case where we had in our case where we had a race condition on balance, we would miss some updates. Here what we'd be doing is creating nodes and then not putting them in the list anywhere, which of course eventually would be a memory leak, and of course just also incorrect because we've lost things that should be in our list. They're no longer in our list. And that was simply done by just interleaving those lines of code, like setting head and then splitting that from this piece down here. So how do we fix that? Well, hopefully it's kind of obvious. You just, somewhere around these two instructions, you just add a lock and unlock, and then somewhere in the list init, you initialize that lock. So you can imagine how that would look. Sorry, I'm off by one with my hands. You would add a pthread mutex here, like here, add lock here, add lock T, pthread mutex T actually. And I won't do this exactly in the code. And then make sure to add a lock and unlock around the code like this. And if you were paranoid and you didn't know what was going on with malloc, would it be okay to put the lock up here? Certainly that would be okay. Why in general would you want to make that critical section, that spot between the lock and the unlock, as short as possible? Yeah. Kind of. I think there's a maybe easier way to say that. Yeah, one of you two. Pick one. Arm wrestle. Yeah, it allows more concurrency, right? It's kind of maybe you were saying that in kind of a different way, which is it allows the threads. Grabbing locks is generally kind of a bad thing, so you don't want to be holding locks for long periods of time, which means you want to have very short sequences of code where you acquire a lock and then release it right away if you can. The larger the lock you have, the more you're preventing perhaps other threads from getting into the critical section and the more trouble you're causing. So let's look at one more example. It's called thread something, hash.c. So it's kind of a simple hash table. It's actually just made of, each bucket just has a list that you kind of add things to. So first thing you do when you insert something is you hash it just with this silly mod function, not a very sophisticated hash table, to a particular hash bucket, and then you insert at that in that list. And so let me scroll up a little bit. So this is a very simple, kind of almost silly hash table. It doesn't even do resizing or anything fancy like that. So you initialize a bunch of lists, and then when you're inserting, you essentially just pick one of those lists based on a hash function like modulo, and then you insert it. So now the question is, how should you add locks? Add a lock to code like this. And how many locks should you add? Since we're short on time, I will not let you think, but rather go with your gut feeling on this, which you may already have. What's the answer here? How many locks should we use when we have a natural structure like this with these hash buckets? Yeah. Yeah, perfect answer. If the list, we already know the list is essentially thread safe, then like the list we just built, for example, then we know this insertion is thread safe, and then this hashing, picking which bucket it is, there's nothing, interesting going on with that. So we could just use a thread safe list. If we didn't have a thread safe list, essentially what we would do is, add one lock per bucket. And sometimes what that's going to allow, of course, is that will allow multiple threads to be inserting keys into this hash table at the same time, as long as they don't collide on a particular bucket. If they do collide, well, of course, then they're going to be serialized. And of course, the more buckets we have, the more locks we would have, so an array of locks. And but this approach would be called like a fine-grained lock approach. It allows many, many locks. We could have just one lock for the entire hash table. That's simpler, but it doesn't allow very much concurrency. So the more sophisticated your data structures get, the more you have to think about locks. So now we're officially out of time, whatever time we're supposed to end at. So we will end, and I will see you next week. Thank you.